let V be a vector space over the field F. F. Which is spanned by a finite set of vectors
So is it from pools?
Yeah. You
Which
want?
chapter? Chapter 3.
Yeah. No. It is chapter 2. UN vector.
I'm telling you the page number.
I don't know exactly
The
what.
section. Anyway, what is the title of it?
This is basis and dimension.
Basis.
Any independent set UM, then any independent
Basis.
set of vectors in V is finite and contains no more than m elements. So this was the theorem that I proved in the last class. Okay, so this is a very important theorem. So there are two corollaries in this theorem. The first corollary is, so what this theorem is telling is, if V is a finite dimensional vector, V is a vector space over the field F, which is spanned by a finite set of vectors, then any independent set of vectors in V is finite and contains no more than m elements. Okay. So this independent set of vectors in V, it cannot contains more than m elements. This is the thing this theorem says. Okay. So, and I proved this theorem in the last class. So there are two corollaries in this theorem. The first corollary is The first corollary is, if V is a finite dimensional vector space, then any two bases of V have the same finite number of elements. So this is the first corollary. So for the proof is very simple. So the corollary is saying that if V is finite dimensional vector space, then any two bases of V have the same number of elements. How can you prove that? Yeah. So
say that each of which can be expressed as a linear combination
of other.
and their equivalences.
Yeah. So U1 u2, un vector. I'm considering this is a basis, and then let's consider another set v1 vector, v2 vector, vm vector. This is another basis of this finite dimensional vector space V. So from the previous theorem, let V be a vector space over the field F, which is spanned by a finite set of vectors, this, then any independent set of vectors in V is finite and contains no more than m elements. Okay. So since, let's first consider this is the basis. Considering this is the basis of V. This set is the basis of V. So this set contains n elements, right? So since the above set is a basis, since u1 vector, u2 vector, un vector is a basis, so the vector space V is spanned by this set, right? Okay. So so by using the previous theorem, we can say that every basis of V is finite and contains no more than n elements, right? That means this m thus if this set v1 vector, v2 vector, vm vector is a basis of V, then m is less equal n. Is that okay?
So any any vector space can have multiple bases.
Yeah, sure.
It's possible. So basis is basically a kind of set from where all the vector elements are derived.
I don't understand.
And conceptually, basis is a set
Yeah.
from where all the elements of the vector space are taken.
Actually,
Does it make
the
sense?
definition is not there. So, see, I already wrote it here, right?
No, sorry, I'm just trying to
Okay.
conceptualize.
Since this is the basis, so the vector space of V is spanned by this set. Okay.
That's
So
the same way, right? So you have a set and you take all the elements from there and so you draw it into the vector
No,
space.
it's not
No.
quite correct.
No.
So there are not all the vectors of the vector space sit on that set. So that is
Why you call it a basis?
you can write any vector as a linear combination of those vectors. That vector may not be in that
Okay,
set.
now it makes sense. So it could be the linear combination of
So
That vector itself may not sit in that.
Okay.
Okay, so I think we solved a problem, right? We solved a problem about there is this problem number 3, I guess, that there's 3 vectors and they span the whole complex number. I proved that theorem problem, right? So since that 3 vectors,
So those are the basis.
yeah, they are the basis, and this C3 is the total vector space. So that 3 vector also inside that vector space C3, but that doesn't mean C3 only consists of only those 3 vectors.
So I can have linear
Yeah.
scaling in those.
Yeah.
So there is a small comment about the article that you are using. When you are writing this in the basis, means that there is no other basis. So if there is a basis, it should be the basis of
That's a good plan. Yes.
Then m is less equal to n. Okay. Now, if I use the same argument and if I take this set v1 vector, v2 vector, dot dot vm vector as the basis of the vector space V, then we can write n is less equal m, right? So yeah. So then we conclude, we can write n equals to yeah. Okay. Okay, so this is the first corollary, and so this corollary allows us to define the dimension of a finite dimensional vector space as the number of elements in a basis of V. So this corollary allows us to define the dimension of a finite dimensional vector space as the number of elements in a basis of V. Okay. So that means if the basis set contains m elements, then the dimension of the vector space is m. Okay. So we can reformulate the previous theorem, and so let me write it as a corollary again. Corollary. Let V be a finite dimensional vector space and that n equals to d of V. Then any subset of V which contains more than n vectors is linearly dependent. Okay, so the first one is, if V is a finite dimensional vector space over the field F, any subset of V which contains more than n vectors is linearly dependent. And this is exactly the we proved it in the previous theorem, right? Because the previous theorem was saying that let V be a vector space over the field F which is spanned by a finite set of vectors. Then any independent set of vectors in V is finite and contains no more than m elements. And for the
I have a question.
yeah,
Where you were saying that it's a finite dimensional vector space. So you are defining the dimension of that vector space to be the number of elements in a base.
yeah.
So when you are saying that it's a finite dimensional vector space, you did not define the dimension yet.
No, I defined the dimension previously.
So here you are saying that later you are defining.
Oh, in this corollary, yeah.
Yeah, but
Number of
but before that you already defined the dimensions.
yeah.
What was that?
So the definition of the
Dimension.
yeah. Okay, it was the field of universe. Let me keep going. Yeah. The space V is finite dimensional if it has a finite basis.
Yes, that's correct. But for that is not the definition of dimension, right?
Yeah.
So that is the definition of a finite dimensional vector space. These finite dimensional we should consider inside an inverted
Yeah.
quotation. These finite dimensional name does not have anything with dimension.
Yeah.
Although the dimensional, one can be confused with the fact that it has finite dimension, but we don't use that. We are defining finite dimensional as long as its basis
Is finite.
consists of finitely many elements. But later, we define dimension to be something else.
Yeah.
But before defining dimension, we have to prove that whatever basis I choose for the vector space, they should all consist of the same number of elements. And that common number of elements is going to be the dimension of that finite dimensional vector space.
Yeah. Right.
Is that correct? Because whenever one sees finite dimensional, one needs to know, is it related to the dimension of the vector space? We are not relating it. So we are saying that the vector space is going to be finite dimensional if it's one basis. Right?
Yeah.
One basis consists of finitely many
Finitely
elements.
many.
But we don't yet say that all the bases of that vector space consists of the same number of elements.
Yeah.
We later do that, right?
Right.
So that was clarification.
So the next corollary is, the next point is no subset of V which contains fewer than n elements, so vectors can span V. Do you agree with this corollary? Yeah. So the first, this one I proved in the last class, the first one, but for the second one, no, I didn't start.
Start down, proof to something.
Okay.
Last week it is in the proof. Yeah.
No, that was another.
If your solution is proof, if your solution and the proof, if your solution after that one is linear.
Yeah, the idea is similar, but that was not the proof related to this corollary. So, for this corollary, so no subset of V which contains fewer than n vectors can span this vector space V. Okay, so let's start the proof. The proof is okay. Suppose V1, V2, Vn is a basis for the vector space V. Now let us consider let us consider another set W1, W2, Wm be a set of vectors in V with image less than n. Now let us proceed by contradiction. Let us consider this set actually spans the vector space V. So for the hypothesis we are taking it as this set spans the vector space V. Then what we can write is, I can write all these vectors by the linear combination of this set, right? Since we are considering W1, W2, Wm, this is a basis of V. Then I can write V1 as A11 W1 plus A12 W2 vector plus A1M W Wm vector, right? Then I can write V2 as 1 2 W1 vector
A21 or A1?
So I want to write it in terms of the row a
But if you write it in A21, so then
So they will be strictly true ones.
no,
yeah, because
I'm
you're
not
taking-
considering it as symmetric matrix because this is not a.
Matrix.
So that is a matrix multiplication, right? That
Still, I'm not defining
but we
is
can
it.
define it as a matrix multiplication, right?
But it depends. I'm just writing all these vectors in terms of the linear combination of these vectors W1, W2, W.
Yeah, I get
Since
that.
I'm considering this is to be the basis of the vector space V.
We can write it as A and stuff to equal to B, right? So if A2 and A3 are equal, then means it's symmetric.
Yeah, that is true.
So then the proof we are trying to do is only also symmetric matrix, and like it's like
No.
that is why I was saying that it is A2.
No, but he can know the definition and let's see what he does.
Yeah. Okay. Good.
So this is 2 2 W2 plus WA 2M. Sorry, sir, I made a mistake
The
here.
first one is mistake here. That's what everybody is saying.
2 A 2M W. And then this is a vector. So there are Vn vector here. So the last vector will be a n1 w1 vector plus a n2 w2 vector plus a nm wm vector. Okay, so I can write it like this: v1 vector, v2 vector, vn vector. This is equal to w1 vector, w2 vector, wm vector with a11, a21, an1. Then a12, a22, an2, a1m, a2m, an. Is that okay? Okay. So now, if I consider this as the matrix A, and so let, sorry, it is already given that, yeah, m is less than n, right? So since m is less than n, the following system has a non-trivial solution. And the system is A11, A12, AN1. Yes, sir. N1 second. What's this?
Okay.
Right?
So then is that A21 or A12?
Which one? Oh, sorry. I made it. This should be 2. Right.
No, you want.
Sorry.
That's
This is
okay.
1.
That's fine. But here,
This one, you're saying?
no. In the last matrix, the one that you're writing, in the first row,
This one?
is that A21?
A2.
Yeah.
Should be 2.
Yeah.
Right. Sorry.
Now you have A12.
1, 2, 8, 2, 2. A, N 2.
Yeah.
And this is A1 M, A2 M, and this is A N M. With x1, x2, dot xn equals 0. So, is this system has a non-trivial solution or not?
Yeah,
Why is that?
because M is not equal to M. Because M is less than M.
Yeah, m is less than n. That means there are more variables in the system than the equation, right?
So can you write that as a vector on the right hand side?
Yeah,
Zero. No.
I understand, sir. 0, 0. Okay. So this system has a non-trivial solution. Everyone agree with that? Because we proved a theorem in one of our lectures that if the system has more variables than the equation, then we can write this solution in terms of the free variables and the leading variables, right? We can write the leading variables in terms of the free variables, and we have this freedom to choose any numbers for the free variable. Okay, so that means this system has a non-trivial solution. So we can set something like x1 equals to b1, x2 equals to b2, dot xn equals to bn. Then if we multiply both sides of this equation, then we'll get v1 vector, v2 vector, vn vector, b1, b2, bn is equals to, sorry, w1 vector, w2 vector.
So that B1, B2 all the way up to Bn is a non-trivial solution.
Yeah, this is the non-trivial solution. Considering this is the
This is A.
sorry, non-trivial solution, and this is the Wm with A11, A21, not that A1, then A12, A22, A2, A1M, A to M, A, M, B1, B2, all the way up to Bm. So the right hand side is what? What is the right hand side? So this is the solution of the system, right? So the right hand side is equal to 0, right? Because this is the solution. Then if I multiply this matrix with this one, then I'll get 0. So that means the right hand side is the 0 vector, right?
The right hand side will be the zero.
We have three elements in the right hand side.
Yeah,
Yeah.
Three matrices. The first one is n component vector,
Yeah.
and the multiplication of these two last two matrices will be an n component column vector.
Correct. This one and this.
And that is an n component zero vector.
Yeah.
All those m matrices are zero.
Yes.
Now when you multiply it with that n component row vector, the result is just a zero, a scalar, right?
So this should be the vector set, right? Because I mean, yeah, right. And
This one zero vector.
it's
Not
just a zero scalar,
Zero scalar.
right?
Do you understand why this is a zero scalar? I think you break it down and write it that.
So
First write that n component row vector, W1 vector, W2 vector. Up to Wm vector. And then you write the column vector. 0. All are 0.
All are zero.
It's an n component 0 column vector, right?
Yeah.
Now you multiply it, and that you get a 0, right? Just a scalar 0. Or I don't know.
it should be a zero vector set.
I think it should be a 0 vector.
Yeah,
right?
because this
Yeah.
the multiplication is W1 vector times
With
0 plus
Right.
W2 vectors
That's
times
right.
0 plus W.
And all the way up to Wm vector times 0, right?
But
So that
0
is-
times W1 is equal to 0.
That is a 0 vector.
So one is zero.
I just wrong.
And it is consistent because the left hand side I'm getting a vector.
Is a vector.
Yeah.
It's a one component matrix, right?
Right. So that means in the left hand side I have a linear combination of these n vectors, but in the right hand side I'm getting a 0 vector. But from the linear dependence, the definition from the linear dependence, we know that if the linear combination is equal to 0 and the scalars are non-zero, then that set is actually linearly dependent. That means this set V1, V2, Vn, we considered it to be the basis of the vector space V, but it is not because this set is linearly dependent.
Daily contradiction.
Yeah. So that's why we get a contradiction, and hence the theory, the corollary is proved.
The basis set cannot be linearly dependent.
Yeah. Basis set has to be linearly dependent.
Independent.
And
The
they have to
other
set
sets
the
will come out of this. Other
Other
linear dependencies will come out. That's the fundamental kind of.
So you can write any vector as a linear combination of those bases from the basis set. There are two conditions for basis. One is that the set is a linearly dependent set, and the other one is that
It has
the
to
set has to span the
Span the
underlying vector space.
So that's
So two two conditions.
So, okay, I can give you an example of this. So, if we consider the vector space R2, if there are two basis elements, the first one is 1, 0, and the second one is 0, 1. And why these two? So, if I write it like this, then this is the basis of this vector space R2. And why is that? Because this set, if I consider it as set S, then this is the basis, because these two 1, 0 plus 0, 1 C1 C2 is equal to 0 only possible.
0, 0.
Yeah, 0, 0 is only possible if and only C1 equal to C2 equal to 0. Otherwise, it is not possible. Right?
What does it do?
So,
It becomes linearly independent.
independent. Because the definition of the linear independence is if you have a set like U1 vector, U2 vector, Un vector, this is the set, and if you take the linear combination C1 U1 vector plus C2 U2 vector plus Cn Un vector is equals to the 0 vector, then this set will be linearly independent if C1 equal to C2 equal to Cn equal to 0. Okay.
This is one of the conditions.
That means, yeah, no. This is the condition of the linear independence. And since this set we can write it in terms of this, but we will get only this 0, 0 vector if we set C1 equal to C2 equal to 0. That means this set is linearly independent.
But it is not sufficient to prove that it's a basis. You have to prove that they also span
Right.
R2, right? Let us do that.
Okay, so for the span, what do we know the definition of the span? So the first definition was the span is the minimal set. Okay, so a set is so it is not working. Okay, the vector space. Okay, let me remove for the definition.
We can span using scalar and different dimension. We can span with
Linear combination.
linear combination.
Yeah. So let
And the space.
S be a vector space S be a set of vectors in a vector space. Vector space V over F, the subspace span by S is defined to be be the intersection W of all subspaces of V which contains yes. So this is the first definition of the span. Then later we proved a theorem that subspace spanned by a non-empty subset S of a vector space V is the set of all linear combinations of vectors in S. Okay, yeah, that was the theorem. So the theorem was the subspace
This kind of recursive definition.
yeah.
The subspace spanned by S is defined to be the intersection.
Yeah, so
all subspaces.
yeah, we started with this definition of the span, then we proved yeah.
This was our definition when we showed that the linear combination.
Yeah. The subspace span by a non-empty subset S of vectors vector spanned by a non-empty subset S of vector of a vector space V is the set of linear space V is the set of all linear combination of vectors in S. So this is a theorem we proved it in the previous class. Okay, so now to show that this set S spans the vector space R2, what we can do?
So this is not empty subset, fine. We set all linear combinations. So we can do all linear combinations to fill up this whole.
No, that is yeah, that I understand, but how can you show that this set S actually spans the vector space R2? So to do
we will take an element and then u and v we will take two elements then alpha plus u plus w is in that space. So we will take these two elements and alpha times one element plus another element. We see that we have to do that.
I mean, you're saying alpha times 1 comma 0 plus beta times 0 comma 1.
So beta is one times beta.
Okay, so what you are proposing?
So we can just we can write beta or we can just only write one. So
No.
in that space.
No, actually, you have to show that in linear combination, this linear combination, we can construct any vector from this linear combination. So what we can do is we can set an arbitrary element of this vector space R2, and that can be like x comma y. Or not, let's not set x comma y. P comma q. So where p comma q is the arbitrary element of R2. So if I multiply this is what? This is alpha comma 0. I think I needed plus beta comma 0, so 0 comma beta, and this is equal to p comma q. And yeah, so
It will become alpha beta. Alpha beta PQ.
right, so that means this pq is a arbitrary vector in R2, and this alpha beta, they are not restricted. You can choose any alpha beta, but where this alpha beta comes from? The field, right? So for us, this is what? This is the field real number. That means this alpha beta belongs to the real number. That means you can construct any vector p comma q just taking this linear combination, right? So that means, so this is not a vector space, you see, this is not a vector space because this is a set, but this vector space span the this whole vector space R2. Okay, and we already defined the dimension of this vector space R2 as the number of elements in this in a basis, right? Since here this number of elements in this set is 2, that means the dimension of this vector space is 2. Okay. Okay, so that was the idea of this.
I have a small comment on the
Yeah.
data. Can you go down a bit? So when you are doing this, so remember when you have to show that vector space is spanned by a certain set of vectors, what you need to show is that you have to start with an arbitrary element of the vector space and show that that can be written down as a linear combination of the elements of the set that you are trying to prove as a basis. Okay. So here PQ is the arbitrary element that you started with.
Right.
And you want to show that that can be written down as a linear combination of these two vectors 1, 0 and 0, 1. In other words, you are looking for alpha and beta such that this equation is satisfied. It's not for all alpha and beta.
Yeah.
You need to show that there exists alpha and beta such that this is fulfilled. And what are those alpha and beta you are ended up with? Alpha is equal to P and beta is equal to Q. And P and Q were the starting point of your attempt, right?
Right.
And then you show that you can find alpha and beta such that PQ can be written down as a linear combination of those two basic vectors, those two elements of the vector space. So it proves that R2 is spanned by these two vectors 1, 0 and 0, 1. Previously, you have proved that these set consisting of 1, 0 and 0, 1 is linearly independent. Now you show that they also span R2, which proves that 1, 0, 0, 1, this set is a basis for R2. And now you already proved that if a basis contains n number of elements, then any other basis will contain the same number of elements. So whatever basis you choose for R2 will always contain 2 elements. And these number, what is it called? The dimension of that finite dimension of the space. So R2 is 2-dimensional. That is why R2 is 2-dimensional. Now we have a complete definition of dimension.
Exactly.
That means this alpha and beta are unique.
Yeah. because just for an example, let's say if I choose 2 comma 5 and root 2, you can write this vector as a 2 comma 5 times 1 comma 0.
Right?
Yeah, sorry, 2.5 plus
0
2
to 2.
times 0, right? So you can reach any vectors by the linear combination of these two vectors.
So you see that the basis of a vector space is not unique. You can choose many bases. But what is unique is the number of elements in the basis, in whatever basis you choose. And that invariant is called the dimension of the vector space.
Yeah. Okay, so now let me state a lemma. Let S be a linearly independent subset of a vector space V. Suppose V vector belongs to V, which is not in the subspace of spanned by S. Then the set obtained by adjoining V vector to S is linearly independent. So this is a very important lemma. So this lemma is saying S be a linearly independent subset of a vector space V, and I'm considering another vector V which is not in the subspace spanned by S, and we understand what it is mean by span, right? So this V vector does not belong to the set S. Okay. Then the set obtained by adjoining V to S is linearly independent. That means I'm considering now this S union of this vector V, and this lemma says that this set is linearly independent. Okay. So how can we prove that? For the proof, let us consider suppose U1 vector, U2 vector, UM vector are distinct vectors. Vectors in S. Also, suppose alpha 1 U1 plus alpha 2 U2 plus alpha M UM vector plus beta V vector equal to 0. So if beta is not equal to 0, then I can write, so I'm considering beta non-zero. Then using the above equation, this I can write beta v vector is equals to what? Minus alpha 1 u1 vector minus alpha 2 u2 vector. So alpha m um vector, right? Then v vector is equals to minus alpha 1 by beta u1 vector plus minus alpha 2 by beta u2 vector plus minus alpha m by beta um vector, right? Everyone okay with this? So right hand side, I'm taking the linear combination of these m elements of the set S. So that means this V, I can write it as a linear combination of the set S, vectors from the set S, right? But in the lemma, it says that suppose V belongs to V, which is not in the subspace spanned by S, right? That means if I consider beta non-zero, then it contradicts the lemma, right? That means this V vector is inside the subspace spanned by this set S. But we consider this vector V that is not in the span of the set S. Okay. So now if we plug in beta equals to 0, then it's simply alpha 1 u1 vector plus alpha 2 u2 vector plus alpha m um vector. This is equal to the 0 vector. Okay.
It equals to 0 if we plug.
Yeah, beta equals to 0.
Yeah, but you are basic.
So I'm using this equation actually in the right hand side of this.
Not this later.
Yeah, right. Then if beta equal to 0, then this is simply what? This equal to 0 vector. But since this set S is linearly independent, that means for every alpha 1, alpha 2, alpha m, these are all 0. So that means if I take the set S union V vector, then the linear combination of this set is this equal to 0 only possible when this alpha 1, alpha 2, alpha m and beta equal to 0, right? Do you understand? Okay. So I'm considering this set S. This is a linear independent set. And S is the set of this vector u1 vector, u2 vector, um vector. Okay. So this set is linearly independent. That means if I take the linear combination alpha 1 u1 vector plus alpha 2 u2 vector plus alpha m um vector, this is equal to 0 vector, implies alpha 1 equals to alpha 2 equals to alpha m equals to 0, right?
They are linearly.
Yeah. So I'm taking, so I'm considering this set S as a linear combination, linearly independent set, right? Now I'm saying is I'm considering another vector V that belongs to the vector space V, and I'm saying this vector V is not, so V is not contained in the span of this set S. Okay. So what is the span of this set S?
Any linear combination.
Any linear combination of the vectors u1, u2, um, right? Up to un. Okay. Now, so now if I consider this linear combination alpha 1 u1 vector plus alpha 2 u2 vector plus alpha m um vector plus beta v vector equal to 0. So I'm just taking this linear combination for now. Okay. So now if I set beta non-zero, then you can write v vector equals to minus alpha 1 by beta u1 vector plus minus alpha 2 by beta u2 vector plus minus alpha m by beta um vector. You can set all these numbers as like c1 u1 vector plus c2 u2 vector plus cm um vector, right? Right hand side I'm taking the linear combination of all the elements of this set S, right? This set S. That means this v vector can be written as a linear combination, but from here we know that v cannot be in the span of S, and the span contains all the linear combination of this set S. So if I set beta non-zero, then v belongs to the span of the set. But the lemma, for the lemma, we said that suppose v belongs to v which is not in the subspace spanned by S, right? So thus we are getting a contradiction, right? Now if you set beta equals to 0, then you are getting what? From this equation, if you set beta equals to 0, then this is simply alpha 1 u1 vector plus alpha 2 u2 vector plus alpha m um vector is equals to 0 vector, right? But we already know that u1, u2 up to um, these are linearly independent. That means alpha 1 equals to alpha 2 equals to alpha m equals to 0, and so for this line we consider beta equals to what? 0. That means this is equals to also beta. So that means this linear combination equal to 0 only possible if all these scalars alpha 1, alpha 2, alpha m, beta are 0, right? So that means, so this linear combination is, so this set is what? S union of v vector, right? So this is,
set is linearly.
yeah, that means this set is linearly independent, right? Now there is another theorem. If W is a subspace of a finitely finite dimensional vector space V, every linearly independent subset of W is finite and is part of a finite basis of W. So I'm considering W is a subspace of finite dimensional vector space V. So every linearly independent subset of W is finite and is part of a finite basis of W. So why is that? So let's prove this theorem. For the proof, so you see, I'm considering W is a subspace of finite dimensional vector space V. Okay. That means suppose if I take a subset, like suppose S0 is a linearly independent subset of W. Okay. So I'm taking S0 is a linearly independent subset of W. Then S0 is also linearly independent subset of V. Is it true?
Seems to
Yeah.
bracket finite, so that means it can be is finite optional. Right?
No.
So you put a bracket.
Yeah,
Finite.
because so I'm considering this to be a finite dimensional, right? So
The last line.
I write here finite to put an emphasis on the finite.
Oh, the bracket is for emphasis.
Yeah.
Emphasis.
Yeah.
I thought it's optional.
S0 is a linearly independent subset of W. Now, is it true that this S0 is also linearly independent in V? Right? Because W is a subspace of the original vector space V. That means if S0 is a linearly independent in W, that means S0 also linearly independent in V. Okay. So S0 is also linearly independent in V. Okay. So since V is finite dimensional, So since V is finite dimensional, can A0 contains more than dimension V elements? V elements, right? It can be equal, but yeah, less than 1, right? So that means S0 cannot contain more than dim V elements. So can we extend this set S0? So this is actually very important here, because you can always find a linearly independent subset, and you can make this subset as a basis of your vector space. So that's why this is very important here. Okay. So I started with a linearly independent set S0. So I can make this subset S0. So S0 is a linearly independent subset of the vector space W, right? So I can make this subset S0 to a basis of the vector space W. How can I do that? So I'm going to use the previous lemma. So the idea is, the first thing I need to do is I have to find a vector V that is belongs to W. Let's consider this W1, and this is inside this vector space W. Okay. And now if this W1 is not in the span of this set S0, right? If this W1, this vector W1 is not in the span of this set S0, then we know from the previous lemma that this set S0 union W1 is a linearly independent set, right? Okay. And if there is no W1 belongs to W that is not in the span of S0, then S0 is what? S0 is the basis of W, right? Everyone okay with this thing? So if there is no vector W1 in W that is not in the span of this set S0, then S0 is the basis of that vector space W. But if there exists a set W1 belongs to W that is not in the span of this set S0, so span of S0, then I can construct a linearly independent set, this, right?
W is this set of basis vector of V, right?
No, W is the subspace of the vector V, vector space V. Okay. So the first step is, if there is no vector W1 in W that is not in the span of S0, then S0 is the basis of W. And if there exists a W1 belongs to S0, is not in the subspace of S0, span of S0, then we can construct a linearly independent set, right? Now this is the first step. So far we discussed what we discussed. This is the first step, and for the second step you have to choose what? You have to again consider this set S0 union W1. Okay, so now let's find out if there is no vector W2 belongs to W. If there exists no vector W2 belongs to W, that is not, yeah, so, and there is another set span of S0 union W. Okay, so if there exists no vectors W2 belongs to W, that is not in the span of W, then this set S0 union W1 is the basis of the vector space W, right? Isn't it?
Basis of that.
W. Do you get the idea? Okay. So if there exists a vector W2, if there exists a W2 that is not in the span of this set, then I can construct another new set, new linearly independent set, and that set is what? Is 0 union W1 union W2, right? So you can do this again and again, and finally you will end up with the step of n step, and that step is the dimension of that subspace, right? So finally after n step you will get a set of S0 W1 union W2 union W, right? Which is a basis for W. So this set is a basis of the subspace W, right? And from this we can see that S0 is what? Is part of the basis of the W, right? Yeah. So that was the theorem. The theorem says that if W is a subspace of finite dimensional vector space V, every linearly independent subset of W is finite and is part of a finite basis of W, right? Okay. So you can always do this this step to find the basis of a vector space or a subspace. What you need to do is you have to find a element W1 first that is not in the span of the set S0 linearly independent set. Then you can construct this set S0 union W1. Then you have to check again, and after n step you will end up with the basis.
Basis of that.
Okay. So there is a corollary again to this theorem, and the corollary is if W is a proper subspace of a finite dimensional vector space V, then W is finite dimension and dimension of W is less than dimension of V. So this is the corollary. Yeah.
It's not equal to
No.
proper.
So you can actually conclude this theorem, corollary from the previous theorem, right? So it says that if W is a proper subspace of a finite dimensional vector space V, then W is a finite dimensional and dimension of W is less than dimension of V. Okay. So let me give you a sketch of the proof. So without loss of generality, we can consider W contains a non-zero vector U. Okay. So I'm considering that W is not empty. So W contains a non-zero vector U, then by theorems, so by this theorem, if W is a subspace of finite dimensional vector space V, every linearly independent subset of W is finite and is a part of a basis of W. Okay. So if we use this theorem, one can construct a basis of W containing U. Right? Is it clear why you can construct this? So because W contains this vector U. So you can definitely construct, and U is a non-zero vector, right? So so then by previous theorem, one can construct a basis of W containing U vector such that the basis contains no more than G V elements. It means that W is finite dimensional and dimension of W is less equal dimension of V. Is it okay? Okay. Now, in the corollary, we specifically say that W is proper subspace of the finite dimensional vector space. That means W cannot be equal to the vector space V, right? So there is a vector U belongs to V such that, sorry, let us consider this as V, such that V is not belong to W, right? This is possible.
Not equals to.
Yeah, because W is a proper subset of the original vector space V, right? So V vector does not belong to a basis of W spanning W. Okay. Hence, by this lemma, we proved here this lemma. We can construct a linearly independent set. So one can obtain a obtain so the set one obtains by adjoining V vector to the given basis of W is a linearly independent set in V, right? I can construct this set because this V is not in the span of the basis of any basis of this vector space W, right?
So, how do we continue?
I think another 5 minutes. Yeah, independent set in V. Then, so what is the cardinality of this set that I constructed here? Yeah, so the cardinality is dimension of W plus 1, right? Do you agree why this is dimension of W plus 1? Because the basis set has a number of elements, what? Dimension of W, and I'm adjoining this vector V that is not in the basis set of the subspace W. So the basis of W contains how many elements?
dimension of the group.
contains dimension of W elements, right? That is the dimension of basis. We define dimension in this way. So that means basis contains the so number of elements in the basis is the dimension, right? So any basis of W contains dimension of W elements. But I adjoin this vector V to the basis of W. So if initially the basis contains n elements, then there is another element. That means there is n plus 1 elements, right? And n is what? N is the dimension of W. That means this is dimension of W plus 1. And it is certainly and since dimension of V is the cardinality of the maximally linearly independent set of V, then I can write dimension of W plus 1 is less equal dimension of V, right? Do you agree?
Maximum.
Yeah. Right? That means this implies dimension of W strictly less than dimension of V. Isn't it? So thus the proof is complete. Okay? Okay. Thank you very much.